Welcome to the 7th of an 8-video series on polar graphing, spirals. First, a quick review about exponential functions. As we all know, exponents are a form of multiplication. 2 cubed is 8, and it's probably not surprising to you that as exponents get bigger, quantities get bigger, and there's nothing new about this. But what happens when exponents get smaller? Well, as exponents get smaller, quantities get smaller. But let's also remember that anything to the 0 is 1, and that anything to a negative power is actually still a positive but very small number. 2 to the negative 10 is a very small number, as you can see in decimal form here. There's nothing new to you probably about this concept, but because it's related to the graphing of spirals, it was worth going over. And just a reminder that these facts are true not only when your base is 2, as it is in all of these problems, but when the base is any positive number greater than 1. Here's our favorite number in mathematics greater than 1. It's called e. You might remember that e is approximately 2.718. Well, the same thing that happens with powers of 2 happens with powers of e. E to the third happens to be about this, and as the exponent grows, so too does the quantity. E to the 1 is itself, of course, and anything to the 0 is 1. Well, just like 2 to the negative power were small fractions, so are e to negative powers. And the more negative the power gets, the smaller and yet still positive the result gets. It's important to note for the spiral graphing that e to a big negative number is a very small positive number. That being said, let's take a look at the equation of a spiral. Spirals are generally e raised to a function of theta, in this case e to the theta over 10 in our particular example. And I like to ask myself the same questions I always do, even when the problems involve sines and cosines. How are changes in theta going to affect r? Well, instead of looking through the quadrants, as there's nothing particularly relevant about quadrants unless you have periodic functions like sine and cosine, I like to look at 3 basic concepts when I graph a spiral. What happens to r when theta is negative? What happens to r when theta is 0, and what happens to r when theta is positive. Now, before we proceed, you may recall that we really haven't analyzed any negative values of theta in any of the problems that we've done so far. And the reason for that is not because negative values of theta aren't relevant, but because in any of the problems you've seen in the videos so far, plugging in a negative value of theta would have given you a point that we had already discovered when we ran theta through positive values. So it's not that theta can't be negative, it's just that it normally doesn't produce any new values, for the periodic functions anyways, like sine and cosine, that we didn't already find for some positive value of theta. In other words, it doesn't normally produce new parts of the graph. However, in this case it will, as we're going to see. So let's analyze this. If theta is a negative number, then based on our brief conversation about exponential functions, r is going to be a small positive number. If I plug 0 in for theta, I get e to the 0, which will give me an r value of 1. And when theta is positive, I should get a large value of r. And more specifically, the larger theta is, the larger quantity I'm going to get for r. Ultimately, of course, I want to ask how these mathematical notions are going to affect the appearance of the graph. So let's get on to that. Notice here that theta is 0 and r is therefore 1. And as theta goes into the positives, r is going to get bigger and bigger than 1, and that's what you're watching here. you're watching theta getting bigger and bigger and r getting bigger and bigger because it's an exponential function. And notice here, I'll stop just past 2 pi. There are no sines or cosines in this equation, so there are no periodic functions that start over at 2 pi. Exponential functions, when theta hits 2 pi, just continue to grow and grow and grow. I'm going to stop here at about 10 radians. At this point, theta is about 10. Remember that 2 pi radians is a complete circle, which is about 6 radians. So it makes sense that 10 radians would be over here somewhere. And when we get out to 10 radians, if you look at the equation and plug 10 in for theta, you'll notice we get e to the 1, which is about 2.7 as shown here. Now I could keep this spiral going, but there's no real need to, because as theta increases, r is going to continue to increase, and we're going to get an infinite outward spiral here. But what's interesting is to watch what happens when it goes the other way. Theta is going backwards now, and right now I'm going by theta equals 2 pi, and right here is theta equals pi. And over here, let me slow this down, over here when I get back where I started, remember I started at theta equals 0. But let's go into negative theta values. As you see in our table, when theta has negative values, r still has positive values. And furthermore, as theta gets more and more negative, r gets closer to 0. And that's what you're seeing here. You're seeing theta become negative, and r, or the distance to the origin, getting less and less and less. And what ends up happening, the more negative you let theta get, the closer r gets to 0. And so you also get an infinite spiral around the origin on the theta equals negative end as well. And that completes the short 7th of 8 lessons.